Hello everyone, I am Professor Anish Vora and I welcome you all in this video lecture. In this video lecture, we will study about one of the combinational logic circuit, and that is a magnitude comparator. But in case of magnitude comparator, in this video lecture, we will study 2-bit magnitude comparator. So let us start with a block diagram for 2-bit magnitude comparator. At the input side, we give two binary numbers A as well as B, and both the binary numbers are with 2 bits. So we have first bit and we have second bit of the binary number A, and that is A0 and A1. Same way we have another binary number and that is B, and we have 2 bits in binary number B. So it is again B0 and B1. So these are known as the 2-bit inputs. We have one binary number A as we discussed, and we have another binary number that is B. So each binary number consists of 2 bits A0 A1 as well as B0 B1, and that is why this magnitude comparator is known as a 2-bit magnitude comparator. In case of magnitude comparator, we compare one binary number with another binary number. So for example, A is compared with B, and we have at the output side we have 3 possibilities. So first possibility, that is a Y1, output is Y1, and the condition is A is greater than B. Binary number A is greater than binary number B. But in our case, we have 2 bits in each number. So we compare A0 A1 with B0 B1. Same way, we have another output, that is Y2, and the condition is A is equal to B. And third possible output, that is Y3, and A is less than B. So at the output side we have 3 different output, Y1, Y2 and Y3, and we have possible comparison, that is A is greater than B, A is equal to B, and A is less than B. So based on this block diagram, now let us check the condition for Y1 as well as Y2 as well as Y3. We are having 3 different outputs. So first condition, A is greater than B. In this condition, output Y1 will be 1. In all other condition, Y1 will be 0. Second condition, that is A is equal to B. In this condition, output Y2 will be 1. In all other condition, Y2 will be 0. And third and last condition, that is A is less than B, and output Y3 is 1. In this condition, in all other condition, output Y3 will be 0. So based on these conditions, now we can prepare the truth table. So truth table for the 2-bit magnitude comparator. At the output side, we have 3 outputs as we discussed. Y1 for A is greater than B, Y2 for A is equal to B, and Y3 for A is less than B. Same way at the input side, we have 2 binary numbers A as well as B. A is consist of 2 bits A1, A0. Same way binary number B is consist of B1 and B0, 2 bits. Now at a time, we will be comparing A binary number with B binary number, and meaning is we will be comparing 2 bits at a time. So for example, 00, A1, A0, 00, we will be comparing with B1, B0, and that is also 00. So we are comparing 00 with the 00, and obviously the condition is Y2 because 00 is equal to 00. Now for the 2 bits, we have 4 different possibilities, that is 00, 01, 10 and 11. Now what we do is, we keep A1, A0 constant and we rotate B1, B0 for all different 4 possibilities. So now what we do is we keep first condition, that is 0 0, constant for A1 A0, and we rotate all 4 different possibilities for B1 B0. So for the A1 A0 we are keeping constant as a 0 0, and we are rotating B1 B0, that is 0 0, 0 1, 1 0 and 1 1. Now we compare 0 0 with 0 0. So obviously A is equal to B and Y2 is high. In all other 3 conditions, 0 0 is less than 0 1, 1 0 as well as 1 1. So in all other remaining 3 conditions, Y3, that is A, is less than B, that is high. So for all these 3 conditions, Y3 is high. For second condition, we have kept A1 A0 as a 0 1, second condition, and again we are rotating B1 B0 for all different 4 possibilities, that is 0 0, 0 1, 1 0 and 1 1. Now we compare 0 1 with 0 0. So A is greater than B, so Y1 is high. 0 1 is equal to 0 1, so Y2 is 1 because A is equal to B. 0 1 is less than 1 0 and 0 1 is less than 1 1. So Y3 is high for remaining 2 conditions, that is A is less than B. Now in the third possibility, we are keeping A1 A0 as a constant and the condition is 1 0. We rotate B1 B0 for all different 4 possibilities, that is 0 0, 0 1, 1 0 and 1 1. Now 1 0 is greater than 0 0, 1 0 is greater than 0 1 and 1 0 is equal to 1 0 and 1 0 is less than 1 1. Accordingly, for the first 2 conditions, Y1 is 1, A is greater than B. For the third condition, 1 0 is equal to 1 0, so A is equal to B and Y2 is high, and for the last condition, 1 0 is less than 1 1, so Y3 is high. And for the last condition, we are keeping A1 A0 constant as a 1 1 and we are rotating B1 B0 for 0 0, 0 1, 1 0 and 1 1. In first 3 conditions, 1 1 is greater than 0 0, 0 1 and 1 0. So Y1 is 1 for all these 3 conditions, and for the last condition 1 1 is equal to 1 1. So Y2, that is A, is equal to B, that is 1 for the last condition. If we check this combination for respective decimal numbers, then we can see that for each combination we have a respective decimal number, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So we have different 16 possibility, and as a whole if we see, then we have 4 different inputs and then we have total 16 possibilities. So this way we can prepare a truth table for the 2-bit magnitude comparator, and now based on this truth table we can have to prepare a K-map, first for Y1, then for Y2 and then for Y3. For the all 3 different output condition we have to prepare K-map. Then from the K-map we can have a reduced Boolean expression, and based on the reduced Boolean function we can implement the logic circuit. That is what or how combinational circuits are designed. So now let us check for Y1. We can have a summation of minterms for which Y1 is high. Now suppose if we check the condition, then for the 4 number, decimal number 4, 8, 9, 12, 13 and 14, we have y1 as a high. Second possibility, that is y2, and that is a is equal to b. Again, if we check the min terms, then for the 0, 5, 10 and for 15, we are getting a high y2. And for the last condition, that is y3, and condition is a is less than b. Now let us check when y3 is high, and that we can take as a min term for preparing the K-map. So we can see that for y3 the numbers are 1, 2, 3, 6, 7, 11. So for these numbers y3 is high. Now based on this output, first we prepare a K-map for y1, and it is summation of min terms, that is 4, 8, 9, 12, 13 and 14. Now we have 4 different input conditions, so we have to prepare K-map with total 16 cells. We have A1, A0 as a one pair of the input. A1 is the most significant bit, and we have another pair of input, that is B1, B0. B0 is the least significant bit. Now we give decimal equivalent number to the respective cells, and that is from 0 to 15. Now we write 1 for the given min terms, so it is 4, 8, 9, 12, 13 and 14. In remaining all cells, we write 0. In next step, we have to prepare a groups. We have one quad possible. We have another pair with overlap condition, and we have still one more pair with overlapped as well as for a wrap around condition. So we have 3 product terms, and if we write product terms for each group, for the quad we can write A1 dot B1 bar. For the first pair we can write A0 dot B1 bar dot B0 bar, and for the third pair we can write A1 dot A0 dot B0 bar. And if we write a Boolean function for y1, we have 3 products, and we can take the Boolean function in SOP form, and that is summation of all the 3 products. So we can write y1, and that is equal to A1 dot B1 bar plus A1 dot A0 dot B0 bar plus A0 dot B1 bar dot B0 bar. Now same way, for the another condition, that is A is equal to B. Now we prepare a K-map for the second condition, that is y2. And y2, that is a summation of min terms, and the given numbers for min terms are 0, 5, 10 and 15. So again, let us prepare a K-map with similar numbers, and we have respective decimal numbers to each cell. We write 1 for the given min terms, and that is 0, 5, 10 and 15. In remaining all cells, we write 0. Now the next step, that is to prepare the groups. But in this condition, we can see that we do not have any possibility to prepare even a pair. So we have to go for isolated groups of 1. So first group, second, third and fourth. And based on these 4 different groups, if we write product terms, then we can write product terms for each groups. In case of isolated groups of 1, we know that none of the variables can be eliminated. So we have 4 different product terms, and if we write a Boolean function for y2, we can have 4 different product terms, and all 4 different product terms are added together. So this way, based on the K-map, we can have a Boolean function for the y2. Same way, we can prepare a K-map for the third condition, and the condition is a less than b. So for y3 we have summation of minterms and the numbers, decimal numbers given, that is 1, 2, 3, 6, 7 and 11. So in similar fashion, we can prepare our K-map. We can write 1 in the given minterms, that is 1, 2, 3, 6, 7 and 11. In all remaining cell, we can write 0. Now next step, that is to prepare a group. Similar to y1, here also we have a possibility of 3 groups, 1 quad and 2 pair. So we have 1 quad, another pair with overlapping condition, and next pair, that is a wrap around as well as overlap condition. Now we can write a product terms for each group. First we write for quad, that is a1 bar dot b1. For the pair, we can write a1 dot a0 bar dot b0, and for the third pair, we can write a0 bar dot b1 dot b0. And if we write a reduced Boolean function for y3, we can write y3 is equal to a1 bar dot b1 plus a1 bar dot a0 bar dot b0 plus a0 bar dot b1 dot b0. So this way we can have Boolean function for y1, for y2 as well as for the y3. We can check or we can verify that y1 and y3 both are complement to each other, and for y2 we have 4 different product terms and none of the variable is eliminated. So we will have to simplify further for y2, and then we can implement our logic circuit. Now let us simplify y2. We have y2 is equal to 4 product terms, but now we can see that from the first 2 product terms we can take common a1 bar as well as b1 bar, and from the third and fourth product term we can take a1 and b1 as a common. So we have taken a1 bar dot b1 bar common from the first and second term. We have a0 bar b0 bar plus a0 b0. From the third and fourth product term, we have taken common a1 dot b1, and we have a0 dot b0 plus a0 bar dot b0 bar. If we do further simplification, we can see that a0 bar dot b0 bar plus a0 dot b0, that indicates exclusive NOR gate between a0 and b0. In same way here also it is exclusive NOR gate between a0 and b0. So if we substitute exclusive NOR gate, then our Boolean function becomes like this: a1 bar dot b1 bar exclusive NOR gate with a0 and b0 plus a1 dot b1 and exclusive NOR gate a0 with b0. Now again, if we take a common the exclusive NOR gate term, then we have our equation like this. So exclusive NOR gate a0 and b0 dot, we have a1 bar dot b1 bar plus a1 dot b1. Now again this term indicates exclusive NOR gate. So if we substitute again exclusive NOR gate, then our equation becomes like A0 exclusive NOR gate with B0 dot A1 exclusive NOR gate with B1. So this simplified Boolean function we can use for implementation of the logic circuit. So ultimately from the K-map we have simplified equation for y1 that is a greater than b, for y3 that is a less than b, and for y2 that is a is equal to b, and that we have simplified. So we can have all the three Boolean function for our ready reference. Y1 we have three product terms and y1 is in SOP form. So we use a NOT gate, we use AND gate, and we use OR gate because it is in the SOP form. We have three product terms. First, we require AND gate with 2 input in remaining two product terms because we have literals 3. So we have to use AND gate with 3 input. We have y2 that is a exclusive NOR gate. We have to use 2 exclusive NOR gate and it is connected in product. So we have to use at the end stage AND gate. And same way we have y3. Again it is in SOP form. We require NOT gate, we require AND gate, and for the summation we require OR gate at the last stage. One product term having 2 literals, so we use AND gate with 2 input. In other 2 product term we have literals are 3, so we require AND gate with 3 input. So with this Boolean function, now let us implement a logic circuit with the help of basic gate as well as with the exclusive NOR gate, a logic circuit for the 2-bit magnitude comparator. We have 4 input variables, that is A1, A0, B1 and B0. Now with the help of NOT gate, we'll have all the 4 input A1, A0, B1, B0 as inverted, that is A1 bar, A0 bar, B1 bar and B0 bar. So first we have A1 bar with the help of NOT gate, A0 bar, B1 bar and B0 bar. So we have 4 input variables as well as 4 inverted variables are available for our ready reference. Now let us start with y1. As we discussed earlier, we require 3 AND gate, and out of 3, 2 AND gates are with 3 inputs. Now as per the Boolean function, we give connection to the AND gate. At the last stage, because of SOP form, we require 1 OR gate, and output of AND gate will give as an input to the OR gate, and output of OR gate gives us y1, and y1 that is a greater than b. Same way, to prepare a circuit for y2, we require 2 exclusive NOR gate. We give input connection as per the Boolean function. At the end stage, we require 1 AND gate. Output of exclusive OR gate we give as an input to the AND gate, and output of AND gate gives us output y2, and that is a is equal to b. Same way, to get y3, we have 3 product terms, so we require 3 AND gate. Out of 3 AND gate, 2 AND gates are with 3 inputs. We give connection as per the Boolean function. At the end stage, we again require 1 OR gate, and output of AND gate will be giving to the OR gate, and output of OR gate gives us y3 output, and that is a is less than b. So this way we can implement the logic circuit for 2-bit magnitude comparator. Thank you for watching my video. Keep watching. Thank you very much.